So, going to continue with Newton's laws and Newton's laws of motion in this unit. We'll continue looking at free body diagrams and how we apply Newton's laws to them. So, one of the other forces that we look at is the tension force. These diagrams can a lot of times be more complex, and which means we need to again pay attention to our frame of reference. And so with that, we need to make sure that we are paying attention to those things. If we pay attention to what our frame of reference is, we should be a lot better at identifying our Newton's second law, Newton's third law, pairs. Paying attention to all those parts will allow us to make sure that we're getting everything right. And when we do these, we again do not just randomly put in things. We do have to pay attention to those. What are we looking at? Are we looking at the forces on the bucket? And we don't have to draw things very elaborate. As you can see here, this is essentially all that is necessary for the free body diagram for the bucket. Now, that's what you see here. These two are going to be what we'll reference as Newton's third law pairs, because it's their equal and opposite, equal in magnitude, opposite in kind of what's handling on what with that. A lot of times it's easier to kind of look at the free body diagram as a vector component as we normally would. And in a vector component, in some cases, they're going to be very much one-dimensional. Only until we start having objects going up a ramp, being pulled along a path, say like a sled, or pushing a lawnmower, or pushing on something, then you have the kind of the added parts of vectors into a free body diagram. But a lot of them are going to be, in some cases, some of them are going to even be, if an object is sliding or moving or pushed along a flat surface, there is going to be some of the magnitudes that you can kind of eliminate. The tug of war is a wonderful example of that, and that in this case, the red flag in the middle is not moving. Why? Because both sides of the rope are pulling with equal amounts of force. Now, this is, I think, a wonderful example of there is not motion until you have one side of the tug of war pull harder than the other. No, I don't know why they're standing so close to the rope. That's usually not probably usually there's kind of an thing, because my guess is somebody would be kicking somebody right in here, playing dirty, so to speak. But what we have is just that. There's no movement in a tug of war until one side is pulling harder than the other. Now, sometimes what happens is the tug of war happens, and as it's happening, it kind of meanders back and forth and that you eventually get, one group going over, and in all reality, what you're seeing with that flag in the middle is to which side is actually pulling harder, which side has the greater force, and that's what we eventually see and look at. So when we have some of these forces, it is important, again, to drawing out what we see. Sometimes the forces are going to be added or they're going to be subtracted based on what's happening to them. So as the 100 newtons, just like the tug of war example, and then 100 in the other direction, the net force is 0. And just like velocity or displacement, when you have them pointing in the same direction, we add them together. What we have in this case is where you have a subtraction, and in some cases this is what we have here is a subtraction, but in sometimes what we saw in velocity is sometimes we would actually have to add a full distance, and those cases are unique. Those are unique circumstances when that does happen. When we see this example here, if Dexter exerts a downward force of 150 newtons, what is the force on the strings? Because we're dealing with the strings, it might be easiest for just that, for us to look at one of the strings. Now, which string do we look at? Do we look at just this one? This one? Do we look at Dexter in itself? It might be best to look at Dexter and then, based off of Dexter's free body diagram, be able to determine what's happening to the strings in itself. So that's what we do. So let's look at the free body diagram of, say, Dexter. And when we draw Dexter, maybe we'll just put a little dot there, a blob for Dexter. After that, it becomes a little bit more, what are we looking at in Dexter and his free body diagram as well. Because we will want to make sure that we also label these appropriately as we look at this. So we know Dexter has about 150 newtons down. So we know we have a kind of a given arrow, or a given for that. And so that's going to equal 150 newtons. But that's not a good enough label for what we want. What is that? That is the weight of the Earth on Dexter. And in some cases, it might be best to not even have that present in your free body diagram, and instead, off to the side, write weight of Earth on Dexter is equal to 150 newtons. Now, Dexter, we still have, there is still going to be, he's being held up, so he's not falling. Because he's not falling, we need to put a total of 150 newtons in what direction? Now we need, because again, there are reason why we need two arrows is that there are two tension forces acting on Dexter. Both of them need to be of 75 newtons, which should, if I draw this out correctly, be half of this other one here, and that's why using a protractor would be very nice. Now, what we have here, though, is a tension, and we can even say T1 and T2, and then are there any other forces acting on Dexter after we have our tensions of the rope acting on Dexter in this free body diagram? So now we could write that the tension of one rope on Dexter is equal to 75 newtons. The tension of two of the rope on Dexter is also 75 newtons because of the whole proximity to where everything is. And because that is what we're looking at, what is the forces on the strings. Now when we get into the actual strings, we can even write a free body diagram for that. And just draw kind of another dot that we would have there. And so from there, we have, we have to go out and let's say, we're going to say rope 1, R1, R2, not D2, but just R2. We then would have a tension of, we'll just say Dexter on rope. And that would have to be 75 newtons. But then there's also still, because again, they're not moving, there is still another tension of the ceiling or whatever's up on top. And we'll just say ceiling on the rope to make lives easier. We just say that that's a ceiling. And again, there should be a equalness to all of the drawings, because again, it's not falling. Dexter's not falling. So in a problem such as this, we again need to figure out, what is going on. In some cases, it might be best to start drawing out what we see before we even do a free body diagram. And so we might have the sign, and that is just that. It is a sign. It is supported by motionless, which is important, ropes. Probably didn't make that very good, but those are 22.5 degrees. Okay, so now we have kind of a picture that we can kind of look at and see and start solving for. Now we can come in, draw a free body diagram for the sine. Because we do know some things. Is one, we know that the sine has a weight of Earth on the sine, okay, and the weight of Earth on the sine is equal to 168 newtons. What we're looking for is the tension, and maybe we'll look at 1 and 2, T1, T2. What is that? Now, what's nice is that both of these are at the same angle. Because they're at the same angle, the tension should be the same. As well. Well, that's not a very good magnitude. There. Now, the angle is 22 degrees, which is, it is an important part of it. Now what we have is a vector problem. In this case, we're not using a Newton's second law yet. We're just solving the vector that we have. Now, which means because we're solving the vector, we can just add our vectors. We can have that. And remember, that's going to be 22.5 degrees. We can then add the other magnitude of, and that should also be at 22 degrees. Now, I have actually forgotten what the name is, but I know that because this angle here is 22.5. I forgot the term that is used, but this angle here is also 22.5, which means that the angle on the inside is actually 45 degrees. So therefore, when we go kind of start labeling some of these, we can say that T2, T1, we then know that, and that would be the weight of the Earth on sine, which we know is, maybe clean this up even more, giving us that angle of 45 degrees. Now, we have the ability to start solving for what we know. Now, when we look at this problem here, and I say look at maybe the law of sine, law of cosine, I don't have any other signs or anything like that. Not only that, there's no guarantee that this is a 90-degree angle or this is a 90-degree angle. So this might work. However, to make life easier to solve, because I know T1 and T2 are at the same angle, it might be easier to create my 90-degree angle and solve, saying that the weight of 168 is half of that, which would be 84 newtons, and then 84 newtons. Now, I could solve for, because I can use the cosine. All right, let's do this up again. We'll use the sine of 22.5 is equal to our opposite 84 over our hypotenuse of T1. Now we have to multiply both sides by T1 to get rid of that so that we can solve for it. But ultimately, still sine of 22.5. Let's go 84 divided by the quantity of sine of 22.5. I put that in parentheses to make life easier for me. It would be T1 is equal to 84 newtons divided by the sine of 22.5 to give a tension. And this is usually where a lot of students look at it and go, there's no way that it's going to be that much. But then you must think about the answer and say, well, if you've ever seen the Olympics and those people that are on the rings in the Olympics, when they are holding themselves straight out, the amount of tension is extreme. As you change the angle, if you're just hanging, yes, the tension should be half. But as you put an angle, as we have, once you put an angle on that tension, it changes and it becomes greater and greater and greater. That's why it takes so much more shoulder strength to change the angle instead of just hanging down. Hanging down is just going to be 84 newtons on each arm, where if you change the angle, it's going to increase and even be greater than your actual weight. So the Olympians that do the rings, that literally make a T with their arms in a free body diagram, would be extremely strong in those shoulders and is, I think, that much more impressive when you see those types of things now. So evaluating your answer, sometimes you have to think about, how could I replicate this? And then you look at it and say, oh my goodness, that would actually it would actually be a greater force at an angle than it would be straight up and down.